Welcome to the course on power electronics with wide bandgap devices. In the last lecture, I have discussed about EMI noises and how you can see these noises in LTspice simulation. Okay. So today I am going to discuss about mitigation of these noises by using the filter. So let's see what I have discussed in the last lecture. So in the last lecture, I have discussed about measurement of EMI noises, and that is possible by using line impedance stabilized network. Already you know about this line impedance stabilized network, which is added the front stage of the converter between supply and the converter. Once we connect this LISN, the values of the LISN are standard values which can be taken from any document. So here it is listed, this LISN values which you can directly use for your simulation. Only thing is that if your converter is different, there you have to see what will be the parasitic parameter, or you can just run the same converter to see whether you will be able to get this kind of noises in the simulation. Okay, so the devices and so both the devices, so basically switch and the diode, they are chosen like this. You can use the same device for your simulation. So now in this case, the noises which are achieved, they are two different noises, CM and DM. So the CM, conductive noise, can be seen in the simulation by considering two lines, adding two lines in, and you can see the resultant FFT. So in LISN, these two lines VLISN1, it is with respect to the LISN connected with positive input and VLISN2 positive, not exactly input, positive line. It is the positive line, and LISN2, it is the LISN with negative line. So that's why we need two LISN or dual LISN. Single LISN will not be able to provide two different line related result. So these two information you can directly get from the converter. You can measure the voltage. You can see the FFT of these noises also, but you will not be able to see conductive and the differential mode of noises. So ideally what we need to do, the first step of designing filter is that first, if you remember the lecture where I have discussed EMI noises, we have to measure. So if I write the steps for designing filter. Step 1 is that we need to measure the noises. By connecting LISN. Step 2, we need to separate two different noises. Now we have noises, but we don't have information of different noises. Separate conductive okay. So this is what is done by considering, like this formula which is used, VLISN1 plus VLISN2 divided by 2 for conductive, and the differential VLISN1 minus VLISN2 divided by 2. So this can be done. So here we are measuring VLISN1 and VLISN2. Conductive mode is VLISN2 1 plus VLISN2 divided by 2, and differential mode VLISN1 minus VLISN2 divided by 2. So this is we are going, so this we will use, and then by choosing the FFT function we can get. So step 3, choose FFT of function of for CM and DM noises. Till this part you have seen in the last lecture. Now we have two different noises, right? So these noises are, this is the CM and this is the DM. Now we have to see whether filter is required or not. How that is possible? So filter requirement is required or not, so that we can get from the standard limit. We need to compare these different noises with the standards given. So the standards are, you already know the standard, CISPR is the standard which we generally follow. There are other standards also, but generally we follow CISPR. So it is also having different like classes, class 1, 2, 3, 4 and then 5. Class 1, class 2, class 3, class 4, class 5. What it tells? So class 1 means it is having magnitude which is much higher. Means standards is having the initial magnitude, it is around 100 dB, and class 5 it is around 50 dB, right? So generally the standards are like, it is followed like this. So if it is like this, so it goes to certain value and then it follows like this, it goes on, right? Now this standard, so let's say class 4 or class 5 if we are selecting. So if you see the previous one, so generally what happens for, let's say class 4 or 5, so generally what happens, this is like standard, it goes like this and this kind of pattern. You can see the exact values from the particular standard website. Okay, so now this looks more or less like this. So for conductive mode noise, if we choose, this is, let's say this is class 4, you need to compare this. So the noise which is achieved in this particular converter, that is well below with respect to the CISPR class 4. Now if we choose class 1, then probably it will be much below than that. So it is satisfying, it is even below in class 4. So there is no requirement of filter for CM. So designing of the filter depends on whether there will be requirement or not. Now there will be requirement with respect to CM or DM. So that is why we need to separate out these noises first, and then accordingly we can decide exactly for what noise we have to design filter, because for CM noise the filter requirement is different and DM noise it is different. For CM noise mostly choke kind of filter we need to use, so that is different kind of requirement, and for DM we can use different type of filter, so that I'll discuss next. So you can see here for this filter is not required. Now if we are choosing this class 4, so for DM filter is required, and then requirement of attenuation you can see here from here. So like how much magnitude need to be attenuated, so that you can calculate. So if it is, let's say 55 or 58, let's say it is 60, so then if it is maximum magnitude is 120, so 60 dB filter is required, right? So that is how we actually calculate the attenuation required. And what frequency, this frequency level also you have to calculate, at what frequency that magnitude, because in all the frequency level the magnitude are not same, so that is why this frequency part is very important. Okay, now we got that for DM we have to design filter, for CM we don't have to. So then what we have to do, we have to then step till step 4, step 3 I have written here, then step 4. So step 3 till step 3 you got the noises. Step 4 you have to find the filter requirement. Compare with standard and see the filter. Step 5, if CM is required filter, if CM, in this case it is not, for CM filter, step 5, step 6, design CM filter. Right. Now step 7, find out attenuation for DM filter. Design DM filter. Step 9, connect all the filters in the network and check with standard. If it is matching, then it's very good. You can use the filter and go ahead to use the circuit. If it is not, then you have to follow the same procedure again and design filter, basically attenuation level you have to select bit higher, and then again design. Follow this procedure until it matches with the requirement. Okay, so in this case, as you know, this two part is not required as it is well below the standard limit. In this case, we have to design the DM type of filter, right? Generally, CM type of filter is like choke kind of filter, and DM you can use different types of filter. So generally, what happens? DM filter, there are actually different filter I have already discussed. What are different filter? Let's say pi type. Okay, so pi type means two capacitors along with one inductor will be presented. This is single stage. And this provide attenuation which is 60 dB. Values obviously you need to calculate based on the frequency where exactly this much attenuation is required. So based on that C1, C2 and L value you need to calculate. Now if it is having double stage, so then you need to connect, means like it again, like whether it will be single stage or double stage, so that depends on the requirement of the attenuation level. It may happen the noise level is very high, for high frequency operation, so then it may happen that you have to use higher attenuation level. So this provide attenuation of 100 dB. See, obviously the values again you have to find out what will be the values of C1, C2, C3, L1, L2, right? Now this provides higher attenuation, this lower. Similarly, there are like filter like T type. So T type means there will be two inductor and one capacitor. So L1, L2 and C. It also provides attenuation of 60 dB for single stage. Now again, like you can use the same thing for double stage. It is C3, L1, L2, L3, C1, C2. So here again the similar like the previous pi type, it provides attenuation of 100 dB. So you can see here basically number of component in both the cases pi type and T type, they are same for 60 dB or 100 dB attenuation. Only thing is that capacitor is replaced by inductor in some case. Like for T type, capacitor is replaced by inductor, right? In inductor is replaced by capacitor. But number of component requirement is same. So it is up to you which one you want to select for your application. Again, there is like basic LC type of filter. So it is like this, right? So it provides attenuation of 40 dB, and then if you again use double stage, so double stage it will be exactly double of the single stage, the component. So here again like it provides attenuation double 80 dB. So you see here, so like different level of attenuations are given. So again like you can go for other types of filter also. So based on this you can choose the type of filter you want to use for your converter. Choose any type of the converter and then calculate the values of this L1, C1, L2, C2, and then use these values in the simulation to see whether it is working fine or not. Okay, So let's open the simulation with filter part. So without filter already you have seen. So this is without filter. So you can see this, like this is having normal LISN and all the parasitic component which are required, so that is presented here. So now we will run this simulation and keep it so that we can compare with the filter part. Okay. So the filter part we'll just open now. And this is with filter. Okay, let's see. So you can see here LCL type of filter is connected. So if I go back to the presentation, so you can check here. So here if you see, so around 60 dB attenuation is required, right? So now that is possible by connecting this, like T type of the filter, as I said, single stage T type of the filter. So this is the one we can connect. So now just open this simulation to show you this simulation file. It is with filter. So this is this. So you can see here this LCL, this T type of filter is added as the filter part. Okay. So now these values are calculated based on the frequency. That calculation you can do by yourself. Okay. Now let's see without filter what are the attenuation. You have already seen this VLISN1 you needed to select, again VLISN2 you needed to select, right? So now you can get the common mode noise and the differential mode noise. This is the differential mode noise. So you see, this is without connecting any filter, the differential mode noise. Now you can see the common mode also. The same thing you just need to replace it with the positive sign. See, this is the common mode noise. It is like maximum time it is well below 40 dB. Some point it is like slightly higher than 40 dB, but maximum like till 100 kilohertz. See, it is like well below 40 dB. And high frequency, then some part it is coming in that. Anyway, like it is well below the standard which we are selecting. So we don't have to bother about this. Now let's see after connecting the filter what kind of noises we are getting. So we can actually try to see in the same plot, so this is the with filter, so the simulation is running now. So you can see this LISN part is there. So in between LISN, so this is like one LC filter is added with the input. So then this part is added, and this is the converter with the parasitic element. You can also refer to the lecture where I have discussed these different filter stages. So I have discussed in the details like which part will be with respect to this conductive type of EMI, which one will be for differential mode EMI. So this different part is discussed in details. You can just refer back that again, and then you can come back to this simulation, and then accordingly you can add the filter. You may also select the GAN switch, right? Where probably you will be seeing if you operate at higher frequency, maybe there is a requirement of common mode field. Then you can consider this choke in the system. Here we haven't connected common mode filter, this for conductive noises, this like kind of filter. Um, so conductive noise related filter, because it is not required. Anyway, this simulation is complete now. So now you can see this is with respect to the output. We can see in output whether there will be simulation, sorry, there will be noise or not. You can see here, so this is after connecting the filter part, this is coming. So basically previously, so I'll just show you with the previous plot, so you can see it together how it is. So this is with respect to the common mode, this is not differential, so let me just need to change this to differential mode, right? So you can see here the magnitude here initially, so it was like starting from this point and then it is going to 120 dB. So in here it is like well below 50 dB in the left hand side by connecting the filter. Okay, so now this values also, like again, like you need to check what values you need for your system. So accordingly you can see whether it is well below or not. Once you have this result, this left side, see with filter, you can compare it with the standard given or standard you are following. So you see the standard, with respect to standard, it is generally starting from here and going down and down, is like this. So then it is, if you see, compare this result, then you will see the entire thing is well below the standard provided. So we can actually consider that okay, fine, this is working fine. So yeah, so this is, so then I mean like your system then is with filter, it is working perfectly fine. Okay, now we can close this window. In case if it doesn't work, right, it may happen, it is not working, then you can choose, instead of T you can choose Y type of filter, or you can change the values of this C, L1, L2 and check whether it is matching or not. And if even if that is not working, you can choose LC type of filter. And then like if attenuation requirement is high, then you can go for the double stage instead of the single stage type of the filter. Okay, so now this kind of filter you can just use, and then if it is working fine, the last step, so basically step 9, I guess, step 9. So then this EMI certificate can be provided for the particular product, because when we are using the system for any application, then this EMI certificate is required. So this EMI certificate, it will be written like what kind of standard is followed for designing the filter. The particular class will be written. Like as you have seen, like as you go towards class 5, the filter is like, filter requirement is much higher as the attenuation is much higher. So then the system will have much less noise. If it is in 1, noise will be much higher. If you go towards 5, then noise will be much less. Then EMI certificate will be provided, and step 6, you can use the product, or maybe end of the filter designing, or you can use the system as product if it is like used for any particular application. Now your work will be use the same simulation for GaN application, or maybe for silicon carbide you can go for higher, much higher frequency, right? So here you can see, so can you show me this, okay, fine. Yeah. So the switching frequency we have given. Okay, we can actually see the simulation, the switching frequency, how much it is selected. So we can go in the simulation again. So the switching pulse we can just see. So you can check from here. So see, this is with respect to 25 kilohertz. This frequency is used. Now, since we are talking about wide bandgap devices, you should go for higher frequency. Now from 25 you go for 100 kilohertz. So can we, okay fine, let me just show you in 100. So if we go without filter one, the simulation part, just close, to close this window. So if we increase the simulation to 100 kilohertz, then this way you can change. And now if you see the simulation results, then you can see that noise level, you can check the noise level. I just wanted to show you for wide bandgap devices how this is going to be different. So now this we have selected 100 kilohertz. Now you can go for 1 megahertz also. You can select GAN device and import the model of GAN here, and then choose the switching frequency as 1 megahertz. Actually vary the switching frequency from, let's say, 25 kilohertz to 1 megahertz, or maybe 100 kilohertz to 1 megahertz, to check the noise level variation and see whether the design filter will be suitable for all the level or not. For if the noise level is high, you will be needing higher value of the filter. Attenuation level will be higher, but that will also work at lower frequency. So you can design the filter at maximum frequency. Anyway, it will work at lower frequency. Like lower frequency, the attenuation level will be much less. This noise level will be much less. That you already know why this noise level will be less. So accordingly you can actually design the filter. So run this simulation for higher frequency and see the noise level. Okay, so let's see how much noise we get here at 100 kilohertz. Okay, now it is done. So let's just see. See, this is with respect to DM noise. So initially you can see this, till this point it is much less. As it is going towards higher frequency, this frequency it is actually shifting the noise part. So this is with respect to the differential mode. Let's just check whether this common mode noises is getting affected or not. See here, so it is actually going bit higher in like 100 kilohertz. Initially it is starting, like you can see here, like till before 100 kilohertz, so the level is much less, but as it goes higher frequency this level is increasing. So now, so like initially, like for lower frequency, this initial part was well below the standard limit. Here probably you have to design the CM filter, so filter for the conductive noise. So let's see with filter, if we keep the same frequency, then it will whether it will satisfy or not. So let's check the with filter part. and simulate. So the boost converter with filter part. So we can just check same like it is 10 4 micro and then this is 10. Okay, let's just run the simulation, then we can get. So the thing is that now without filter you have seen that initially it is below the standard, but after some time it is increasing. So if I go back here, so if I tell you while the simulation is running, let me just tell you this part. So see here, so this is for the common mode noise, right? So initially till let's say some point, this is this filter, like the magnitude is higher, means this particular part, if you see this particular part, basically initial part, the magnitude is higher as the frequency is increasing. So after some point, so the exact frequency point you can get from the standard itself, because there the exact frequency point is given. Here I am just giving you idea that how it looks like exactly. So then after some point this magnitude decreases, but in the simulation as we are increasing the frequency, so initially from this point to this point it is below the magnitude which is provided in the standard. After some time this magnitude is increasing, so in this particular part the magnitude is higher. So then what you need to design filter in this particular part considering the frequency. Then in this particular part the frequency is higher, right? Frequency is much higher. So then what will happen, your filter size may be lower, but you will need filter for this particular region. It may happen that you will need filter also in this particular part, but again like higher frequency it is, so the filter if you design for this particular part, it may satisfy the filter requirement of this particular part as well. Okay, so this is the difference. So like for lower frequency you needed filter in this particular part, right? Then it moves to the second part. It may happen if you choose the further higher frequency, it may move towards the third part. So like this, like as you are going for higher frequency, the filter requirement with respect to that also will increase at higher side frequency. Then the requirement of the filter will be probably at high frequency, so size will be less, but requirement will be there. Okay, so that you need to see. So let's just see whether the simulation is complete or not. So this is done now. So let's just see this like with filter whether it is satisfying, because you know we have designed it for lower frequency, right? So initially like at 25 kilohertz. Now we will be seeing this filter with respect to the high frequency. See, it is like now in this frequency also you are getting this result, right? So this filter is satisfying, because see you have already designed the filter for low frequency. Anyway it is capable of attenuating signal, which attenuation at higher frequency, right? It is, see this particular point, it is well below the standard limit, so it is satisfying, so there is no problem. But if you sometime it will happen that if you design the filter for high frequency, it may not satisfy the requirement of low frequency attenuation. So that you have to check based on your application. Again, like some application the variation of, like in control frequency variation is there, but for some application frequency variation is not there. So if frequency variation is there, then you have to choose like different stages in frequency to design the filter. If frequency is constant, then you have to choose only single frequency to design the filter, so then you can get the actual value. Okay, so this you can actually design. So you use any of the device and design the filter for EMI requirement. Okay, that's all for today. Thank you.